So Stephanie Casey is our next presenter. She comes to us from Eastern Michigan University, where she is a mathematics teacher educator and specializes in statistics education. Stephanie has done extensive professional development workshops with mathematics teachers. She assures me that she gets along well with science teachers because her husband is one, okay? So she's going to share with us how teaching data analysis in science classrooms.
Thanks. Hi, everybody. Like he said, I appreciate you guys inviting somebody from the other side of the tracks, this math teacher up here, to be with you guys. But I can play nicely, so all's good. So I'm here to share two big ideas with you about the idea that even though you are science teachers, you're actually teaching statistics as well. And so therefore, I'm going to share with you some ideas about teaching data analysis in science classes. So first off, we're going to play a little game called Determine the Source, Next Generation Science Standards, or Common Core State Standards for Math. So in this game, I'm going to show you a series of slides in which there's going to be a standard listed on the left and a standard listed on the right. One of them is from the Next Generation Science Standards. The other is from the Common Core State Standards of Math. Which is which? You decide. Okay? So first round we have on the left, compile all the boiling point measurements from the class into a line plot and discuss the distribution in terms of clustering and outliers. On the right, we have comparing two or more data sets, such as the lengths of mung bean sprouts for plants with no direct sunlight versus the lengths for plants with 4 hours of direct sunlight per day. So think for a moment. If you will please raise your hand with one finger if you think the one on the left is Next Generation Science Standards, and raise your hand with 2 fingers if you think it's the one on the right. Interesting, very interesting. Now I hear there's some authors of the Next Generation Science Standards out there, so I'm really curious if they get it right, and if you know who they are, you might want to take a peek their way to see if you got it right. The correct answer is Next Generation Science Standard was number 1, which I will say in perusing the room was the lesser chosen one out there. Most of you picked 2. So this already is reinforcing my number 1 idea that look how much similarity there is between what we're asking students to do in the math classrooms and what we're asking them to do in the science classrooms. And in particular, this one is showing that it's the same idea of looking at one variable and seeing how that distribution plays out. All right, for our next round, we have option number 1 on the left. This table, given in the margin, which I'm sorry I didn't have room on the slide to share with you, shows percentages of U.S. residents who have health risks due to obesity by age category. Students should be able to explain what the cell percentages represent and provide a clear description of the nature of the association between the variables obesity risk and age. Sorry, that was a long one. Okay, option number 2. Use data in a two-way table as evidence to support an explanation of how social behaviors and group interactions benefit organisms' abilities to survive and reproduce. All right, marks, get set, go. Put up a 1 if you think Next Generation Science Standards on the left. Put up a 2 if you think it's on the right. Okay, you guys are getting smart. A lot of 2s out there, and you are correct. But please, I hope that you still see there's a lot of similarities here. Both of these are talking about looking at data in two-way tables. The context which the Common Core State Standard mentioned was obesity. You know, this is certainly a very relevant topic in the science world. All right, we've got one more round, so let's see if we can stick with our trend of getting better at this with our third round. Here we go. Option number 1 on the left. Interpret the slope of a linear model of 1.5 centimeters per hour as meaning that an additional hour of sunlight each day is associated with an additional 1.5 centimeters in mature plant height. Option number 2, fit a linear function to a data set showing the relationship between the change in temperature of an insulated sample of water and the number of identical hot ball bearings dropped into it. Find the slope of the graph and use it to determine the specific heat of the metal. All right, let's see what you think. Which one is the Next Generation Science Standard? Is it on the left? Show a 1. Is it on the right? Show a 2. Oh, we got a lot more mixes of 1s and 2s on this one. Not so confident. All right. Survey says next generation science standards, number 2. I don't know. Mathematicians don't often talk about hot ball bearings, but that's interesting. We would do that. Anyways, again, look how similar these are. These are literally talking about the same idea. We've got data, bivariate quantitative data that we've got a scatter plot of. We've created a linear model for that, and we need to interpret the slope of that graph within the context of the problem. Literally the exact same idea, both worded in the standards using, scientific examples. So what's my big idea number 1? There is a lot of overlap between what's in the Common Core State Standards for math and the Next Generation Science Standards. There's synergy when you bring that teaching together. So use that to your advantage. Through that little game, I hope I've made you believe that there's a lot of similarities in their core ideas that the two have. But it's not just the ideas, it's also the processes. What does it mean to do math? What does it mean to do science? So I want to show the overlap between those as well. So I've highlighted for you 2 of the practices that are in the Next Generation Science Standards. Practice number 3, planning and carrying out investigations. And practice 4, analyzing and interpreting data. Okay, so what does it say in practice 3? We start. We ask a question. We decide what data need to be gathered to answer that question. And then we plan our study in order to collect that data to answer our question. Continuing on in practice 4, once we have the data, we need to analyze it and use that analysis, including graphical, display data, summarize, numerical, statistical things, and explore relationships and then come to conclusions. Okay? Now, in the Common Core, there's also the teaching of statistics in mathematics. Stats is rolled into the math. And there is a statistical investigation process that is emphasized starting in 6th grade, and they continue all the way through high school. What does it mean to conduct a statistical investigation? That is the driving point behind the statistics standards in the Common Core. This is a graphic trying to show the same idea as well. So we start upper left-hand corner, we pose a question. Upper right-hand corner, we have to collect data to be able to answer the posed question. Bottom right corner, we analyze that collected data. And then bottom left corner, we interpret our analysis in order to be able to answer the original posed question. Oftentimes, not only do we try to answer the original posed question, but in reality, we somewhat answer that posed question, but it actually generates lots more questions. And then that leads to this cycle. So that's why this graphic is trying to show this as a process that is cyclical. One leads into the next, etc. Again, notice how much overlap there is between what we are doing when we do the scientific process and what we're doing when we do the statistical investigatory process. So much overlap. So use this to your advantage. It will support your students' learning, and it will support your teaching. We've already heard about the curriculum dragon, breathing down our throat. You have so much to cover, so much to do. Well, let me tell you, math teachers feel exactly the same. So why are we not working together? We are honestly teaching a lot of the same stuff. So work together to fight that dragon, bring them down, work with those math teachers, cross the divide, say hi, start collaborating. The more we can do to work together, the better it is for our students. What's so funny is our students are the ones going from class to class to class to class. They are seeing the connections. What happens to us as the teachers is we just sit in our little siloed room and we aren't out there connecting with those others. And so we need to do a better job as teachers. I mean, one of the most informative things I did when I was a teacher was shadow a student for a day. And when I did that, I really saw all these connections across the way that had such potential that unfortunately the teachers weren't acting on because they didn't know that there was all those connections. So I am telling you, those connections are there. It is up to you guys to act on them. So that was my big idea number 1. Big idea number 2 has to do with variability. So let me just start with a little story to give you some historical perspective. So in the early 19th century, science had a very much clockwork universe perspective to what truth was about the scientific, our world. They said, okay, science can perfectly describe the world around us. Things like Newton's law of motion and things like that, okay, this tells us precisely what things are and how they work. As we continue to get better instruments that can give us more precise measurements, we're going to have less error in what we're doing, and things will be more exact, and voila, we will have described our universe. Well, in actuality, what happened throughout the 19th century is they did develop those instruments that did make more and more precise measurements, but instead of it eliminating the error, actually there was more and more error that was created. They found that those measurement differences actually grew rather than diminished. And that's what forced a push now in science to get on the bandwagon with the statistical models perspective, in that variability is going to be present in data. It's inherent. It's reality. And so what we need is statistics in order to be able to wrestle and deal with the variability that is inherent in data. So there are three big sources of variability in data, and I think it's really important to teach students about these sources so that they can better understand and make sense of this idea. So number one is natural variability. Objects of study are inherently different. So for example, if I'm trying to say how tall are females in America, there's variability to that because not every female in America is the same height. So that's the idea of natural variability. We also have measurement variability. So this arises from variation in repeated measurements of the same attribute of the object of study. Here's a really fun activity to do. Have the students in your class, one by one, come up and measure the circumference of your head, the teacher. My head size isn't changing. It is what it is. You go back, you collect that data, you will not believe the variability in their estimates of how big around my head is. And so that can really bring out this idea of measurement variability. It is inherent. You guys probably know when you have your students doing those science experiments, they're getting a lot of different answers in there, right? And it's, that is the reality. Sure, we need to get better at making precise measurements, but the reality also is even with precise measurements, you're going to have variability. So we need to teach them how to deal with that through statistics. And then lastly, induced. This is exactly what you do in science. You put the objects of study into experimental and control groups so that they have differences in their experiences that's supposed to hopefully induce very different results by the time you're done. All of these, again, inherent in statistics and really important in science as well. So we need to help our students learn how to use statistics to make sense of scientific data, which inherently will have variability. And that's why we need that statistics in the science classroom. Thank you.